Opinions expressed on this radio station, its programs, and its website by the hosts, guests, and call-in listeners or chatters are solely the opinions of the original source who expressed them. They do not necessarily represent the opinions of Revolution Radio and FreedomSlips.com, its staff, or affiliates. You're listening to Revolution Radio, FreedomSlips.com, 100% listener-supported radio, and now we return you to your host.
Ladies and gentlemen, welcome back to another episode of Cosmic Catastrophe on Revolution.radio. I am your host, Diamond, from the Oppenheimer Ranch Project, and joining us today, as usual, is my partner and co-host, Leah Shaper.
Hello.
Welcome to the show. It's going to be
I actually have my mic on this time.
Excellent. It's going to be a great show. The title of the show is Dark Matter Does Not Exist, and the universe is 27 billion years old. Do you have any cursory thoughts before we begin?
Yeah, but I think we should just get into it.
All right, we're going to first start with the discussion about the failure of science at the highest level. And what I'm talking about here is tens of billions of dollars have been dumped into the search for dark matter. And we're going to go over all the experiments and all the failures. Guess what, Leah?
It maybe doesn't exist.
Yes, they haven't found any of it.
I mean, here we are. We've been proclaiming for decades, we don't know what it is. We don't really understand its nature. It doesn't interact with any electromagnetic forces. We can't see it. We don't have any direct evidence for it, and yet it exists. It has been the contention for decades.
Can you see the screen share?
Yes.
All right, so for decades, we've been stuck with the lambda cold dark matter Big Bang hypothesis, and that's what we're looking at here. And what it assumes is that at some point in the past, and they usually assign that 13.8 billion years ago, there was a singularity, and then it exploded, and at that moment, all matter in the universe was created. Mm-hmm. That sounds plausible, right? So, to bring you up to speed, there's a problem that everyone has known the entire time about this hypothesis, and you're looking at it right here. Mm-hmm. And this has to do with stellar velocity with distance. And what this means, and what this graph shows, is that when you look at a galaxy, the further away you get from the center, the speed of the stars continues to increase. Mm-hmm. That completely goes against the lambda cold dark matter Big Bang theory, because what that expects is that there will be a short increase in speed away from the center, and then the further away you go in the galaxy, you should see decreased speeds. Mm-hmm.
Which incidentally is what we see in our own solar system with our planets.
Exactly. So on a solar system scale, this also occurs, yes. Mm-hmm. But on the galactic scale, it does not happen. Mm-hmm. So intrinsically, what this means is that we don't know gravity.
Yes, exactly. Right, but this is the whole reason for deciding essentially, the way I look at it anyway, is that a decision was made at some point that dark matter has to exist in order to make our observations consistent with our equations. It's like literally like there's just a missing piece in our equations that we don't understand. And so we decided that this dark matter exists in order to make our equations work, but we can't detect it. It doesn't interact with any electromagnetic forces, et cetera, et cetera.
So yes, what Leah is saying, in order to explain why the observation doesn't match what is expected, is that there is a boogeyman.
Mm-hmm. Right.
Called dark matter. And it gets even more insane. We'll get to it in just a few seconds, which I think that this graph will blow your mind. But according to the lambda cold dark matter theory, dark matter constitutes 26.5% of all the mass, energy, and density of the universe. And the remaining 4.9% is actual matter.
Well,
So,
and then don't forget that there's also a huge chunk of that that is dark energy, like
Yeah,
76, whatever the number is, 70 something percent,
yeah, let's get this graph.
68.3%. So, another form of essentially dark matter, assuming that energy and mass are indeed interchangeable, essentially.
Right. And based on this, as a scientist, what this means is that we know about the universe is only 4.9%. That's how much we know about the universe. The rest is completely made up. Because what has happened over the last several decades is billions of dollars of money have been dumped into finding this fake boogeyman. The Large Hadron Collider cost $4.7 billion to build, plus an estimated 13 extra billion for the CMS and ATLAS detectors. And none of these experiments has found any dark matter. And so scientists have created multiple fairy tales to explain this dark matter.
I mean, the saddest part about this, right, is, somebody made an observation that essentially recognized the boogeyman, right, the missing part of the equation in the 30s. And instead of going back and re-examining our understandings of gravity in particular, this was just like invented. This concept of dark matter and dark energy was just invented, and I find that tremendously sad. Like, was it really that difficult to go against the flow and re-examine how we had been describing gravity? I mean, that's sad. The resistance is just insane.
Right. So some of these dark matter candidates have been weakly interacting massive particles, which they named WIMPs, of which they've never found. They also came up with massive compact halo objects, which they call machos. Can you imagine getting billions of dollars to make up these crazy acronyms?
Right.
There also was the hypothesis of axions and sterile neutrinos. And in order to search for these types of dark matter, quote unquote, they did several experiments at the Large Hadron Collider, including, but not limited to, CREST, CRESST, which was cryogenic rare event search with superconducting thermometers. And then there's the Lux Zeppelin experiment, a couple more $1 billion there. And then the Axion dark matter experiment, and then the Xenon dark matter experiment. And then after all of these experiments, they didn't find a single particle of dark matter.
It's like, it's almost like an exercise in keeping academic cosmologists in business. I mean, I'm not trying to, like, well, I guess I sort of am. I'm not exactly trying to insult cosmologists per se, but I don't. This is one of those things where you get your head so deep into a field that you can't take a step back and just re-examine some basic concepts, and then you just end up with a whole wing of science that's like a comedy of errors. It's just so frustrating to witness, and that you can't see that while you're working on that. I just don't get it.
Right. And in doing research for this podcast, it came to my attention that alternative theories as far back as 1983 have existed to explain the strange graphs, that the observed graphs that we're getting about the speeds here.
Yeah.
And their explanation is that there is a change in Newtonian dynamics the further away you get in the galaxy.
Which is really interesting in and of itself, right? Because maybe this isn't correct, but ideally you would think that the laws of physics would be constant throughout the universe. But essentially what this is suggesting is that that's not the case.
Yeah, and interestingly enough, I looked at a Hawking paper, Stephen Hawking, God rest his soul. His interpretation of the universe is kind of like infinite, but it's not. It's a giant bubble. And as you get further out, let's say, 100 billion years towards the edge, there's no time. There's less time ceases to exist at a point. So it's a weird infinite universe, and time only exists in certain density regimes within the universe.
That's an interesting concept. I can sort of imagine that, like, especially with describing that as a bubble that you essentially never get to the edge of, right? Because time stops existing.
There is no time.
Which is actually kind of interesting. Like it could, I mean, we don't have to get down that far down this road, but it could help sort of explain this issue that you and I have raised many times. Like, if there's an edge to the universe, then what's on the other side, right? Like, how do you have a bubble of space that's not also within space, right? Like, this is sort of the issue. But yeah anyway.
So, and this ties in well with the redshift blunder. That goes all the way back to 1915.
Yeah.
So
go ahead.
I'm just going to read the abstract. As light travels extreme distances through space, its frequency slowly diminishes or attenuates. And we observe this phenomenon as redshift, the tendency of visible light to drop towards the red end of the spectrum. Unfortunately, for over 100 years, redshift has been misinterpreted as Doppler effect. This is the fundamental cosmological error that creates the fatal flaw in these misconceived hypotheses like Big Bang theory, expansion theory, Hubble's law, the Hubble constant, dark matter, dark energy, black holes. It's all fairy tales. And when you look at make the actual observations, none of these fake theories hold water. When you start looking at galaxies, the speed at which they're moving away from each other varies. And that is impossible in any of their made-up Big Bang cold dark lambda models.
Yeah. I mean, with this paper, very clearly, I love this paper. It's such a short paper. It's very simple. It's very concise, and it explains the problem perfectly. You cannot treat redshift like Doppler, because redshift refers to light waves and Doppler refers to sound waves, and light and sound propagate in entirely different ways. They're not the same thing. You can't treat them the same. So the other part of the problem here is that any particular star at its source, may be emitting light in the blue range, in the yellow range, and in the red range. If you do not know the frequency of the light at its source, then you can't determine anything by redshift. So a blue star that's very far away might appear red by the time it gets to us, but it's also possible that it only shifts to yellow, or that it was in the red wavelength range in the beginning at its source to begin with. It's also and still appears red when it gets to us. So you cannot determine anything about the speed at which it's moving or how far away it is. It's also possible that, let's say you have a star in the red wavelength, and it's so far away that the wavelength gets so long by the time it gets to us that we can't even see it. So we can't even detect the star. So and then this plays, it's not the entire picture, but it plays a huge role in how we determine expansion of the universe, distances away that stars are, and the speed at which we're traveling. But we're typically not. Well, here's just a little paragraph from this paper that I think is just kind of brilliant. Unless one knows the frequency of light emitted at source, there is no way to know by how much it has been redshifted by the time it reaches the observer. For over 100 years, astrophysicists have not paid enough attention to frequency at source. They falsely assume that what they are witnessing are galaxies in motion and mistakenly use redshift to indicate a presumed velocity of motion. This is the logical error of circular reasoning, that is, inadvertently including one's conclusion in the assumption, then using the assumption to prove the conclusion. If we know the frequency of light at its source, then redshift lets us know how far away that source is. There is nothing else that redshift can tell us. But again, if we don't know the frequency at the source, it doesn't mean anything.
Yeah, so just here alone, what we're talking about is major problems in cosmology to go back 100 years.
Right. And then all of these other things built on top of it. It's like building a skyscraper with a faulty foundation.
Right. And in decades, almost every new discovery by cosmologists have baffled them because their model is so incorrect and they're incapable of changing their model. Now, everything they find is baffling them, including, but not limited to, all of the new images from the James Webb Space Telescope. The images are so mind-boggling. Some astrophysicists were crying when the images came out because it meant that their entire career was based on a lie.
Right. Right.
None of these, they found a spiral galaxy 10 times larger than the Milky Way. And based on Big Bang cosmology, the galaxy should have only been 400 million years old.
Mm-hmm. Right. Yeah. Just a few days ago, I had a very brief conversation with somebody on X, who I don't know what their background is, but seemed to be trying to represent cosmology in some way. And I said something about the redshift issue and that, given that this is a large part of how we determine distance and rate of movement and expansion of the universe and all of that, and that we're not using it correctly, there's a problem there. And this person's like, well, we use all of these other techniques. We look at cosmic microwave background radiation. We look at gravitational lensing, blah, blah, blah. And I'm like, okay, yeah, I get that. Like that's not the entirety of the picture. I said, but something's wrong here. Why do we keep having to dramatically change our estimate of the age of the universe? And then it was like conversation just ended right there. It's weird.
Well, fortunately, there are some new models, not only the modified Newtonian dynamics model, that is referred to as MOND, M-O-N-D. That was first postulated around 1983 by Mordechai Milgram. And it basically is a modified gravitational force law, where the further you get away from the center of mass of your galaxy, Newtonian dynamics changes.
Right.
And that's completely believable.
No, that is completely believable. And it's partially because we only get to test Newtonian dynamics within a Newtonian dynamic system, right? Like we don't have the ability to get way far away from a system that would use Newtonian. I mean, we live in it. We don't have the ability to space travel in a way that gets way beyond any gravitational objects. And so we have no way of knowing whether or not those rules still apply in that situation. I mean, they may or may not.
Right. And so Mordechai Milgram, he teamed up with Jacob Bekenstein, and they came up with the concept of AQUAL, which is a quadratic Lagrangian. Mm-hmm. All these words.
Yeah, I know.
But when they did the case study, I think they looked at 150 galaxies or whatever. Their conclusions based on this new model, which is modified Newtonian dynamics, matched the observed curve.
Yeah. Right.
It's like Occam's razor. How come cosmologists in 1983 through 85 didn't start looking into this?
Right.
Makes no sense.
I gotta point this out because it really made me laugh. So you sent me some articles for the layman about this dark matter may not exist issue, and one of them is from Cosmos magazine in March of this year, and the opening paragraph mentions, that this physicist has come out with a new contentious hypothesis. The cosmos doesn't have any dark matter in it. Like that sentence on its face is kind of ridiculous, right? Like the contentious part is that this thing called dark matter that we've never been able to detect and doesn't interact with anything else that we can detect in the universe. That saying that doesn't exist, that's the contentious part. Are you kidding me? And then towards the end of the article, they're talking about another professor in Queensland, and granted, her comment was about Gupta, who's the scientist that came up with this theory to explain the universe without dark matter. She was actually referring to a previous paper that he wrote that determined that the universe is actually, what was it? What is it? 27 billion years old?
26.7.
Okay, yeah, so roughly 27 billion years old. She's referring to that paper, but she says extraordinary claims require extraordinary evidence. You have to go and test it in different ways. And it's like, extraordinary claims? Like, why not apply this to dark matter? Like, isn't dark matter an extraordinary claim? This thing that we can't detect and we don't understand in any way, shape, or form, and yet we continue to pretend that it does. Isn't that extraordinary? Like lacking, and we have no evidence for it at all, except in our math.
Well, right? It says a lot about the state of science. For decades, the idea of consensus science has been shoved down our throats.
Yeah.
And now most of the science writers believe that. They believe things like dark matter exist because they've been around for 100 years, the concept of it. Unfortunately, the reality of science is that everything is a hypothesis that's being tested. So any new idea that fits the model better or fits the observation better is the better model. And so back in 1983, modified Newtonian dynamics, MOND, was a way better model explaining that explained the observations, and they didn't even use it.
Right. You know, when I was doing my master's program, which I never finished, in biomedical writing, and I was doing this largely for the science writing aspect of things, and my sort of advisor professor, you know, really pushed this idea that science writers could essentially be like a check and balance for science, right? That they're sort of in a unique position to be standing outside of a field, you know, in the process of understanding and digesting it, and then potentially writing about it for a layperson or other scientists. And they have the opportunity to kind of like double check facts, things that might blind that a scientist might be blinded by simply because their head's too far into it. And I really lament the fact that that's not what science writing has become. It's just become this like some of these articles, they don't even really explain anything for the layperson. It's just this like regurgitation of what another scientist is telling them without any real understanding of what the heck they're talking about. It's weird. It's really unfortunate as I see it. Your mic is off.
I couldn't agree more. Some more problems with the James Webb, the advent of the James Webb Space Telescope, are these giant structures that are being found far out at the edge of the quote unquote universe. Some of these structures measure 100,000 or millions of light years across.
Yeah.
And how long does it take for a structure like that to form?
Mm-hmm.
The universe is so mind-boggling.
Yeah. I think our understanding is really elementary. And I, you know, another thing, you know, I find it really intriguing that Gupta's new theory really does rely on this idea that, like, let's say, like the just as a simple example, the gravitational constant of the universe wouldn't in fact be constant, right? That the like as we just discussed, essentially the laws of Newtonian dynamics would be different at the far ends of space or whatever. I don't really personally buy that concept at all, in the sense that I think any truly elegant, truly explanatory theory of the universe should be scalar and consistent across all uh, all domains, right? I already have a problem with the fact that we use different systems to describe the universe at different levels. We use quantum dynamics to explain the microcosmic level. You know, we use Newtonian dynamics to explain kind of the mid-grade level. We use relativity to explain the macroscopic level, et cetera, et cetera. And none of these theories jive with each other. You can't use them together very well. You can't use one theory to sort of explain everything. And the fact that the laws are changing depending on where you are and how far out into the universe, to me, that screams of this is not the right explanation. And that's just kind of like at a gut instinctive level. I get that reaction, but I trust that immensely.
Well, Don Scott from the Thunderbolts Project explains it all using Birkeland currents and plasma at every
Right.
scale.
Right.
From the galactic scale all the way down to the atomic scale. The same thing is happening at every scale.
Right, which is one of the reasons that I find electric universe theory absolutely fascinating. But of course, there's a huge amount of resistance to this in the scientific community because it upends, decades and decades of, theory and data blundering and all, people who things that upon which scientists' careers have been built over many decades. Like, I get that on a human level that there's going to be some resistance to something that upends the entire structure of what you've been working on your whole life. I get that, but isn't truth more important?
Exactly. Let's get to we'll transition to the EU model and the Thunderbolts project for the end, because let's talk about the new model that basically says there's no need for any of this dark energy or dark matter.
Right. Which I will say is a start, right? Like at least this person is trying to iron out, let's say, the kinks in the math, right? Like there's a hole in the math that leads us to conclude dark matter. And it's like, well, that doesn't jive, right? And this person at least is trying to rectify that and has sort of found a way to do it. And maybe from here somebody can move into a place where this will all make much more sense. But
yeah, so dark matter, the term used in cosmology, refers to the elusive fairy tale substance that does not interact with light or electromagnetic fields and is only identifiable through its gravitational effects, unless we don't know about gravity.
Right.
Now, despite its mysterious nature, dark matter has been a fundamental element in explaining the behavior of galaxies, stars, and planets, even though we've never been able to find a single particle of dark matter.
Right.
So, at the heart of the research of Rahendra Gupta, he's up in Canada somewhere, right?
Yeah. I forget where exactly.
But he's a distinguished professor at the Faculty of Science. Gupta's innovative, how do you say that? Innovative approach involves the integration of two theoretical models. One is CCC, which is covariant coupling constants, and the other is TL, which is tired light, known together as the CCC plus TL model.
So just for our viewers and listeners, the covariant coupling constants is this idea that the constants, the universal constants, are not actually constant, that they are different, let's say, at the edges of the universe. And the tired light idea is it's the idea that light is losing energy the further that it travels over very extended distances, which is similar to redshift.
It makes complete sense, too, because all light starts at a source.
Mm-hmm.
And if it travels a billion light years, I think it's going to lose some energy there.
Right.
So,
well, I mean, here's the thing, right? Like, any object that loses momentum or loses energy in the course of travel is because it's dealing with opposing forces, right? Like, so just in the simple Newtonian model, it's the force of friction that's going to slow it down. And the absence of friction, there would be no slowing down at all. There'd be nothing to stop it. So there would be no loss of energy. So, theoretically here, with light losing energy as it travels, it has to be encountering some kind of resistant force. Now, part of the problem with this is that we treat space as if it's like completely empty and that there's nothing there.
Which is
So
completely ridiculous.
right. Right.
Now, cosmologists have known that the Big Bang cosmology has been wrong, even though they came up with the Hubble constant. When they tested it and made observations, the Hubble constant was not constant anywhere. They
Right.
got different values when they made different observations. And so they renamed it the Hubble stress, because it's all about just making up fairy tale terms to explain away why your model does not match the observations. That's bad science. It's bad science.
Yeah.
So the way they go about running these models is they come at cosmology from a different point of view completely, which is what needs to happen. You need fresh new hypotheses to move forward in science.
Yeah. Yes, absolutely. And you know, even if they're not totally spot on, and I don't think that I suspect that this theory is not, at least there's some forward movement in terms of recognizing and dealing with some of the blunders in our theory in the past.
Yeah, and this is a pretty new paper, March of this year.
Yeah. Yeah.
So did anything stick out in the paper that you want to cover?
No, I mean, I honestly, I didn't read it very carefully because a lot of it is the actual math, which I no longer have in my head in work like this. So it's just not really feasible for me to digest this.
Yeah, this is the whole
you know,
paper.
if I was still in college, yeah, I could digest it, but it's been a long time. So but I get the basic concept. Yeah.
This is one heck of a quadratic equation. Jesus. Well, what is interesting is take a look at this paper. This paper just came out 5 days ago.
Yeah. Yes.
And this is based on observational science. So this is what we need to do in order to create a new theory for cosmology. We need to do more observational science. And instead of being baffled, we need to maybe change directions. So now we have new theories where dark matter is not required. And then a few people look out and they find 6 spiral galaxies that don't have dark matter because you don't have to use any fake numbers.
Yeah. Yeah. No, and it's interesting too, because right, the idea of dark matter really does come out of this concept that what we observe of galaxies is that the exterior elements of the galaxies, the ones that are furthest away from the center, actually move faster than the interior ones, right? As we were discussing in the beginning of the show.
Yeah.
And this is part of where the dark matter thing comes from. And so what they found with these spiral galaxies is that they weren't operating that way. And so it eliminated the need for the dark matter to explain that motion. So that's pretty interesting.
Well, and it also,
and I'm gratefully simplifying here, but
but it also leads to the idea that we don't know gravity.
Yes.
And that some galaxies behave different than other galaxies.
Yeah. Yes. And you and I have talked about this and pondered this for a long, long time, that, I mean, frankly, gravity in and of itself, it also like lacks real definition and understanding. You know, it's some unseen force that has only to do with mass and distance. And it's just a mathematical equation, but we don't really know what it is. You know, it's not something at least partially tangible like light, or actually tangible like matter. We don't know what it is. It's invisible to us. It's just a mathematical equation. So maybe that is the problem here, that maybe it's not what we think it is. It's just represented in our math, and we don't know where that comes from.
Right. And just like the Hubble constant is not constant, we know that gravity is not constant either.
No.
In
not
a
on
single
Earth
place,
and not in the universe, apparently.
If you go, if you change your altitude, the amount of gravity changes. If you look at a map, you can look at gravity anomaly maps. There are gravitational anomalies all across our planet.
Mm-hmm.
So something is controlling the gravity, and we do not have any idea what it is.
No.
But if we live in an electric universe, all of this can be explained through Birkeland currents and electrical potential. And Donald Scott explains that the reason some spiral galaxies may fit this lower curve as opposed to a lot of observed galaxies that fit this upper curve is the electrical potential at the Z pinch. So it would be based on voltage, which then equates to velocity as you move away from the pinch.
Yeah.
Some galaxies, the majority of them accelerate away from the Z pinch.
Yeah.
But they don't all have to do that based on the voltage.
Yeah.
And the voltage might also control the amount of gravity.
Yeah. I mean, it's the difference between having essentially a purely mechanical model versus one that is based on electromagnetics. I mean, this is a very different way of looking at things, but I really do think it has the potential to explain a lot of the variability we see, and also, as we discussed, to provide a consistent scalable interpretation of the universe.
Right. And as our technology has gotten better and better, guess what happened? We started seeing things that shouldn't be there.
Yes. Right.
And it was baffling scientists that all of the stars in our universe are connected along filaments.
Mm-hmm.
And so you've got EU out there, Thunderbolts Project, plasma cosmology, all that's out there. The IEEE uses plasma cosmology as its cosmology.
Mm-hmm.
And cosmologists are baffled at what they're seeing here. They can't explain the filaments. That's almost like a college graduate not knowing how to tie their shoe. How can you explain that?
Even at a gut level, that seeing this should imply elegance in the universe should be very obvious. Like the scalability thing, speaking of scalability, I mean, what does this resemble? It resembles neuronal structure, right?
Absolutely.
Like at a gut level, there's something so inherently elegant about that it should scream at you that there is some very important truth in this that you should be looking at.
Yeah, and the further out you look, the more obvious that everything is connected.
Right.
Everything.
Clearly.
Even at our local scale, we can show how connected. This is our local bubble called Laniakea, and the filamentary structures exist at every scale.
I'm actually not clear. How are we getting these images? Do you know?
Well, what you do is you look out into space at different wavelengths and take pictures at newer and higher resolution wavelengths.
Okay.
And within the last 10 years, these filamentary structures showed up.
Right.
Like we recently got pictures of the galactic center of the Milky Way and found plasmoids and filamentary structures.
Right. Speaking of space not actually being empty, clearly it's not empty.
No, it's filled with Birkeland currents, and on these currents are coaxial, co-rotating regions of voltage.
Yeah.
And it's also where all of the elements in the universe are generated. And it's scalable. Like as you go to the edge of a galaxy, you have more hydrogen in the stars than towards the center where there's heavier metals like iron. And in the middle where there's more lithium in stars.
Mm-hmm.
And looking in the same Birkeland current study that Don Scott's model looked at, the same thing occurs. So at the stellar scale, just look at our sun. If our sun is the Z pinch of the Birkeland current, the surface of the sun is hydrogen and the heavier elements are inside.
Right. But I mean, you can almost look at it as if part of it is like a density thing, right? If you're looking at the surface, you're maybe looking at less density, but in an area where there's more density, you have more opportunity for particle interactions, which then provide the opportunity to create heavier elements.
Charge density.
Right.
Yeah.
Right. Well, and then, the other part of this too relates back to what we were talking about earlier. If it's really true that light loses energy as it moves through space over extended differences, if you want to think about it in terms of friction, all of these other plasma is rarefied gas. It's particles. Those are going to create friction. Those are going to slow light down. So
Absolutely.
yeah.
Absolutely. All right. So if the universe is an infinite filamentary structure with unlimited energy, where did all this energy and stuff come from?
Right.
That's the question. But if it's infinite, it was already here all the time. And what we're seeing, because we can't conceptualize infinity, but let's say it this way, over trillions of billions and trillions of years, which is a tenth of infinity, which is not true, but you're getting my point here. This is the level of organization that infinity has gotten to. It's absolutely mind-boggling.
Well, mind-boggling,
It's
astounding.
taken forever to get this level of organization.
Literally forever. Well, it's weird, right? Because when you get to that level, infinity in terms of time and instantaneous become the same thing. Do you know what I'm saying?
Yeah. So this moment is infinity, and it keeps happening. And then, so if you have any doubt about the idea of a higher power or the presence of God, it is what you're looking at.
Yeah.
It is the macro structure that is so organized that took forever to get this way, that contains all energy, information, knowledge, matter, everything. And it's all connected, which means at any moment you can tap into all of it. Like, that is incredible.
It is. And it speaks very much to, I think, something I've believed for a long, long time, that God is energy, and that also is love, and it is bliss, and it is existence, and it is infinity. It's all the same thing. It's interesting because there's almost, I've thought about this a number of times, there's almost a parallel to a very crucial, what is really a Christian concept. It's the idea of constant creation, that at any given instantaneous moment is a creation by God. Now, that idea was disrupted by Newtonian mechanics tremendously, right? Because Newtonian mechanics said, that like what I was saying earlier, that an object will have inertia and it will keep moving unless something stops it. Like, so everything becomes cause and effect along this like chain of time. But this way of looking at the universe really is as if the universe is being created again and again and again and again and again at every instantaneous moment, which personally I sit with much more comfortably these days. And it sort of helps eliminate this issue of, well, if the universe is expanding and it has an edge, so what's on the other side? If the universe, began with the Big Bang at some particular moment, then what happened before that? It kind of eliminates all of that. Does that make sense? I don't know if I'm explaining it very well.
Well, also, when you look at the high level of organization, because we're talking massive, thousands and millions of light years here just in this little picture.
Yeah.
The presence of imaginary things like black holes can't exist because of how intricate this filamentary structure is. It would break it apart.
Right.
But the concept of space travel long distances in short periods of time seems very possible along these large Birkeland currents. Especially if they're coaxial, co-rotating electromagnetic fields. All you would need is an electromagnetic vehicle that knew how to capitalize on the Birkeland current.
That's interesting to think about. Yeah.
And then you could instantaneously be at another place if you entered there.
Yeah.
Essentially.
Yeah. Right.
Maybe
so it almost provides some background structure.
Go ahead.
It almost provides some background structure for the idea of a wormhole.
Yeah, that does. So wormholes can exist, maybe.
Maybe.
They're not sucking anything in. They're just
No, and I'm
long
not thinking about a
distances.
wormhole
Yeah.
in the idea of that it's like some tunnel through space and time. I mean, I'm thinking about it the way that you suggested, that some kind of electromagnetic vehicle could almost provide like an um
Frictionless.
what?
Frictionless.
Right,
So
ship
there would
from
be
one
no
place to another, which
G-force.
interestingly fits actually in pretty well with some of the concepts in quantum mechanics, right? That a particle can just suddenly disappear and show up somewhere else. And all we understand is its probability of doing so.
Maybe they find little Birkeland currents and just take a fun ride.
That's what I'm suggesting. Yeah.
So that goes back to the double slit experiment, right? If you've got
Kind of.
a piece of wood with two slits and you shoot a million BBs at it, on the other side, you get the same pattern, two slits when the BBs go through the holes. But if you take light and shoot it through the slits, you get 5 or more bands.
Right, you get an interference pattern that, this is so funny that you brought this up. And I was thinking about this right before the show. Two completely separate people last week said to me that the double split experiment was about observation changing results. And I said, no, that's Schrodinger's cat. Double slit literally just illustrates that light acts as both a particle and a wave. That's really funny that you should bring that up. It made me go back and just review the double slit experiment and to say, like, what part of this is about the observation? And the only part of it that is about observation is in the way that any experiment involves observation. You can't do it in an experiment without observing it, but observing it doesn't change the results. That's only the case in Schrodinger's cat.
And quantum mechanics.
Which is it's the quantum mechanics issue essentially that I just said, right? That a particle can show up somewhere else. Its probability of doing so, we can understand that, but its probability of showing up in a particular place is also affected by our observing it, which is very bizarre.
Right, and the observer's intention can also alter the results.
Right.
The intended result can be gotten by two different observers intending two different things, and both get the intended results of the same. It makes no sense.
Well, okay, but it also does make sense in terms of I forget the Japanese researcher's name, the guy that did the experiments on water. And our emotional intentions on water and how it actually changes the structure of the water. So that would suggest that there's a direct link between the quantum mechanics element and the energy that we are carrying in our bodies, which again leads me back to God is energy, love. It's all of those things are the same.
Well, expanding on this concept, that would mean that the soul is not just in humans and animals, but also trees and rocks and water,
it's the whole universe,
and oceans and rivers. Everything has a soul, a different version.
And there's a name for that. It's called panentheism. It's not just pantheism, which is, I forget which way it goes. God is in everything or everything is in God. But panentheism it goes in both directions. God is in everything and everything is in God.
I think I'm a panentheist.
I am. I have been for a long, long time.
Yeah, that's a very interesting structure.
Yeah.
All right, so the beautiful thing about knowing all this and how big it all is and unimaginable is that nothing really matters. This will continue to go on forever, whether we're alive or not. And we will continue to be part of this infinite energy. We just shift form.
Mm-hmm.
Yeah. And the only thing that we're really observing, humans, is in these 3 dimensions. We really don't know about higher dimensions or anything else. Which is the sad part.
Yeah.
And maybe only entities like us can exist in the denser regions because we're at the edge of the galaxy, where we're traveling the fastest, and our gravity is suitable for life. Maybe if you go towards the center of the universe, there's no gravity or something, and there can be no. There's so little we know.
Well, and you said it was sort of sad that we don't perceive other dimensions, but maybe it's not, right? And this comes out of very strong spiritual beliefs that I have, that we incarnate into this universe as human beings because we chose to, and that we continue to incarnate after we die, because we decide that there's specific things that we need to learn. And, you know, maybe it's just a function of that. You know, we are just these particular kinds of souls, these energy forms that feel a strong need to learn something about the universe from this particular perspective. You know, maybe there's some point where we incarnate as some other being that can interpret dimensions 5, 6, 7, 8, or whatever, because at that point, that's particularly what we want to learn. I think that there's something to learn from every particular perspective in the universe, you know? Even if we may itch to learn more than we're capable of perceiving.
Yeah. And so, what do you think about the robots killing us all? So here's a thought experiment. If we can now see 27.6 billion light years into the past, twice as far as we thought the universe was, it clearly means the universe is much older, and we've made a good argument that it's infinite, so it has no age, because there's time is a localized effect that only we are experiencing, because every moment is infinity. When they looked out there with the Hubble telescope and they found a Milky Way-like galaxy that has 10 times the mass as ours, how many Earth-like planets there with people or entities just like us existed 27 billion years ago?
Right.
There's 10 times the chance of planets like that being there than in our galaxy, and it was here 27 billion years ago. And we think that we're advanced? Like, come on. That's mind-boggling.
This is a bit off topic to what you were just saying, but you said something earlier that alluded to it. And I just wanted to throw out the idea that in one respect, the concept of the Big Bang may not entirely be wrong, in the sense that, like, it's in the sense of that any particular moment is both instantaneous and infinite at the same time. And it sort of goes back to this constant creation idea. It's like, it's almost as if, I have such a hard time articulating this, but it's almost as if there's like a Big Bang happening at every given instantaneous moment. Does that make sense?
With no explosion?
I don't know how to articulate this correctly.
Okay, so the concept of the Big Bang is that at the moment of creation, all matter formed. So that means that every moment, everything
is a Big Bang.
Is.
Right. Every moment is a Big Bang.
Without a bang, though.
Right. And it's like, it's more metaphysical than it is physical.
Yeah.
I suppose. But again, it's recreating the whole thing again and again and again and again.
It's kind of hard to,
It's a little hard to wrap your head around, but.
Well, guys, if you want to come see Leah and I, we are going to be at the Crestone Energy Fair September 14th and 15th in the San Luis Valley in Crestone, Colorado. We are going to have an interactive seed saving and permaculture booth, and we're going to have other stuff like some of our merch to give away. We might have some herbs or something that we jar up.
I'll be selling my jewelry.
You'll be selling your jewelry, which you just won the blue ribbon.
I got a first place prize at the county fair.
You win a nickel, right?
It's like $1. $5 maybe? I can't remember. I think it's $1.
Well, you hit the big time.
Whatever. It's just nice to exhibit your work
and to participate in the community.
Yeah.
Whether it be the local community or Laniakea at large.
Yeah.
How many biological entities live in our local bubble?
Right. I mean, that's a really good question. I mean, given the infinity of the universe, I find it impossible to think that there aren't other intelligent beings out there. I feel like the chances of that are by its very nature, by the very nature of infinity, are that the probability of those beings not existing is zero.
Is zero. So everything that's possible that you can think of has happened.
Yeah.
Which means that there are civilizations that made it past a 26,000 year clock cycle on our Earth that kills us all pretty frequently due to bombardment or magnetic excursion. There has to be a civilization that is now billions of years old. That is mind-boggling. What do they know? They would be able to control the energy of an entire galaxy. They would be able to manipulate it. They may be even able to manipulate large portions of the universe.
Well, no, but maybe, okay, we've talked before about the 26,000 year cycle as Yuga cycle as being a process of forgetting, right? Like we have to forget everything we know in order to continue to learn, so we can like learn all over again. Maybe those beings are living in a part of the universe where that cycle is a different number. Maybe it's that cycle is 100 million years.
Wow.
Find us tonight on Magnetic Reversal News on YouTube at 8 p.m. Mountain Time, 10 p.m. Eastern.
That's boom.
Listen to Revolution Radio at freedomslips.com. And we'll be right back after this message.